Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a really fascinating area, the idea of Potemkin understanding in large language models. It's a provocative concept, so let's unpack it. Who wants to kick us off?
I can start. The term Potemkin understanding, it immediately brings to mind the historical anecdote about Potemkin villages, facades built to impress Catherine the Great. The core idea is that these LLMs, which seem incredibly sophisticated on the surface, might be exhibiting a kind of simulated intelligence. They're really good at generating text that looks meaningful, but are they truly understanding what they're saying?
Right. It's the age-old question of whether these models are just sophisticated pattern-matching machines or if they're actually grasping the underlying concepts. I mean, they can generate amazing prose, even code, but do they know what it means? Can they reason about it in a way that a human can?
And that's where it gets really interesting, because it touches on what we even mean by understanding. If a system can convincingly answer questions, generate creative content, and even pass certain kinds of reasoning tests, is it fair to say it understands, even if the underlying mechanism is fundamentally different from how a human brain does it?
Exactly. It gets into the philosophy of mind, doesn't it? Are we defining intelligence by its output or by the internal processes that generate that output? And more importantly, if it is just pattern matching, what are the limitations of that approach? Where does it fall apart?
Well, one area where it seems to fall apart is in situations requiring genuine common sense reasoning or the ability to adapt to novel situations. LLMs are trained on massive datasets, but they're essentially interpolating from that data. If they encounter something truly outside their training distribution, they can produce bizarre or nonsensical results. It's like they're confidently bullshitting, even when they have no clue what they're talking about.
That's a great analogy. And I think it highlights the limitations of purely statistical approaches. They're incredibly powerful at identifying correlations, but correlation isn't causation. They can learn to associate certain words with certain concepts, but they don't necessarily understand the relationship between those concepts. They lack that deeper symbolic understanding that humans possess.
And that lack of causal understanding really hurts them when it comes to dealing with the real world. These models are trained on text and code, but they don't have bodies. They don't interact with the physical world in the same way that humans do. They don't understand gravity, friction, or the basic laws of physics, except through the lens of text descriptions. So, how can they truly understand anything in a meaningful way?
It's the embodiment problem, right? They're disembodied intelligences, which makes it difficult for them to ground their representations in the real world. But let's dig a bit deeper. What are some specific examples of this Potemkin understanding in action? Has anyone seen a particularly egregious case?
Oh, I've got a good one. I was experimenting with one of the larger models, and I asked it to write a story about a cat chasing a mouse. The story started off reasonably well, but then the cat suddenly started flying. And when I asked the model why the cat was flying, it gave me some convoluted explanation about the cat having special abilities due to quantum entanglement. It was complete nonsense, but it was presented with such confidence and grammatical correctness that it almost sounded plausible, if you didn't think about it too hard.
That's hilarious, and it perfectly illustrates the problem. They can generate grammatically correct sentences and even mimic different writing styles, but they don't have any real-world knowledge to constrain their output. It's like a really talented actor who can deliver a line convincingly, even if they don't understand what the line means.
I saw a similar example with a coding task. I asked the model to write a simple program to sort a list of numbers. It produced code that looked syntactically correct, but it was incredibly inefficient and would have taken forever to run on a large list. It had clearly learned the patterns of sorting algorithms, but it didn't understand the underlying principles of computational complexity.
That aligns with my thinking. It's like they've memorized the surface features of intelligence, but they haven't grasped the deeper principles. So how do we address this problem? Is it simply a matter of feeding them more data, or do we need a fundamentally different approach?
I think more data will definitely help, to a point. These models are still relatively data-starved compared to the amount of information that a human brain processes over a lifetime. But I also think we need to start incorporating more structured knowledge into these models. Things like ontologies, knowledge graphs, and logical reasoning systems. We need to give them a framework for understanding the relationships between concepts, not just the statistical correlations.
I agree. I think we need to move away from purely data-driven approaches and towards more neuro-symbolic methods. We need to combine the strengths of neural networks with the strengths of symbolic AI. Neural networks are good at pattern recognition and learning from data, while symbolic AI is good at reasoning and representing knowledge. By combining these two approaches, we can create systems that are both powerful and interpretable.
I think we need to go even further. I think we need to fundamentally rethink how we represent knowledge in these models. Current deep learning models are essentially giant lookup tables. They map inputs to outputs, but they don't have any real understanding of the underlying structure of the world. I think we need to develop algorithms that can represent knowledge in a more spatial and temporal way, that can understand how things relate to each other in space and time.
That's interesting, Donald. Can you elaborate on that spatial and temporal representation idea? How would that work in practice?
Well, think about how humans perceive the world. We don't just see a collection of pixels, we see objects in space, interacting with each other over time. We understand that objects have persistence, that they move and change according to certain rules. Current AI models don't have that kind of understanding. They treat each image or each sentence as a separate, independent event. I think we need to develop algorithms that can track objects and events over time, that can build up a rich, dynamic representation of the world.
So, you're talking about incorporating something like a world model into the AI, a simulated environment where the AI can experiment and learn about the consequences of its actions.
Exactly. And that world model needs to be fundamentally spatial and temporal. It needs to understand how things move and change, how they interact with each other. It needs to be able to predict the future based on its understanding of the past and present. And it needs to be able to learn from its mistakes, to refine its understanding of the world over time.
That sounds incredibly complex, but also incredibly promising. It's like giving the AI a sense of intuition, a way to anticipate events and reason about the consequences of its actions. But how do we even begin to build such a system? What are the key challenges?
One of the biggest challenges is representation. How do we represent spatial and temporal information in a way that's both efficient and expressive? Current deep learning models use fixed size vectors to represent everything, which is clearly inadequate for capturing the complexity of the real world.
And that's where I think neuroscience could provide some valuable insights. The brain uses a variety of different coding schemes to represent information, including distributed representations, sparse coding, and temporal coding. Perhaps we can borrow some of these ideas from neuroscience to develop more sophisticated representation schemes for AI.
That's a great point. And I think we can also learn from how the brain integrates information from different sensory modalities. The brain doesn't treat vision, hearing, and touch as separate, independent streams of information. It integrates them into a unified, coherent representation of the world. We need to develop AI systems that can do the same thing.
And that integration needs to happen at multiple levels of abstraction. We need to be able to translate between different coordinate systems, from the low-level pixel representation of an image to the high-level symbolic representation of an object. And we need to be able to do this seamlessly and efficiently.
It's a huge challenge, no question. But I think the potential payoff is enormous. If we can build AI systems that truly understand the world, that can reason and plan and adapt to novel situations, then we'll have achieved something truly remarkable.
Absolutely. It could revolutionize fields like medicine, education, and manufacturing. But let's not get ahead of ourselves. We're still a long way from achieving true AGI. But understanding the limitations of current approaches like Potemkin Understanding is a crucial step in the right direction.
Definitely. Recognizing the problem is half the battle. And by focusing on things like neuro-symbolic integration and spatial temporal reasoning, I think we can make significant progress towards building more intelligent and robust AI systems.
Yes, and even if we don't achieve full AGI in the near future, these efforts will still lead to valuable advancements in areas like robotics, natural language processing, and computer vision.
So, what are some concrete research directions that could help us move beyond Potemkin Understanding? Let's each suggest a specific area that we think is particularly promising.
I'd say we need more research into unsupervised learning techniques that allow AI systems to learn about the world without being explicitly trained on labeled data. The brain learns primarily through unsupervised exploration and interaction with the environment. We need to develop AI algorithms that can do the same.
I think we need more research into knowledge representation and reasoning. We need to develop formalisms that can capture the complex relationships between concepts and that can support efficient and reliable reasoning. I'm particularly interested in exploring the use of probabilistic logic and Bayesian networks for representing uncertain knowledge.
I'd advocate for research into spatiotemporal algorithms, looking at how biological systems process space and time, and attempting to translate those algorithms into computational models. We need to understand how the brain represents and manipulates spatial and temporal information, and how it uses this information to guide behavior.
And from my perspective, I think a key area is bridging the gap between neuroscience and AI. We need to develop more biologically inspired AI architectures that incorporate principles from neuroscience, such as hierarchical processing, distributed representations, and feedback loops. I'm particularly interested in exploring how attention mechanisms in the brain can inform the design of more efficient and robust AI systems.
Those are all excellent suggestions. It sounds like we have a pretty clear roadmap for future research. It's an exciting time to be working in this field.
Absolutely. It's a challenging but rewarding field, and I'm optimistic that we can make significant progress in the years to come.
Agreed. The potential benefits are enormous, and I'm excited to see what the future holds.
Well, that's all the time we have for today. Thanks for joining us for this exploration of Potemkin understanding and large language models. Hopefully it's given our listeners some food for thought. Join us next time on Cognitive Spirals as we continue to delve into the mysteries of mind and machine.
One thing I think is important to mention. You can see the limitations of this type of understanding if you ask an LLM to explain something that requires a multi-step reasoning process. I recently asked one to explain how a car engine works, and while it gave a decent overview of the basic components, it completely failed to explain the order in which the different parts interact to produce power. It couldn't describe the cycle of intake, compression, combustion, and exhaust in a coherent way. It lacked the understanding of temporal sequences that's crucial for grasping how an engine actually functions.
That's a really insightful example. It highlights how these models struggle with understanding processes that unfold over time. And it points to the need for AI systems that can reason about temporal causality, that can understand how events lead to other events in a predictable sequence.
And it's not just about understanding temporal sequences, it's also about understanding spatial relationships. Think about how a mechanic diagnoses a problem with a car engine. They don't just look at the individual parts in isolation, they look at how those parts are arranged in space, how they're connected to each other. They understand that a broken hose can cause a loss of pressure, which can affect the performance of other parts of the engine. That kind of spatial reasoning is crucial for understanding complex systems.
It's about understanding the interconnectedness of things, the way that different parts of a system influence each other, and that requires a level of abstraction that current AI models simply don't possess. They can identify patterns in the data, but they can't understand the underlying causal mechanisms that generate those patterns. That's why they often fall apart when they encounter situations that are slightly different from what they've seen before.
And that's also why they're so vulnerable to adversarial attacks. You can often fool these models by making subtle changes to the input that wouldn't fool a human. For example, you can add a small amount of noise to an image that causes the model to misclassify it, even though the image still looks perfectly clear to the human eye. These models are relying on superficial features rather than genuine understanding, which makes them easily tricked.
Right. They're exploiting the weaknesses of the model, the gaps in its understanding. And that's why we need to build AI systems that are more robust, that are less reliant on superficial features and more focused on underlying principles. We need to build systems that can reason about the world in a way that's similar to how humans do.
Which brings us back to the importance of spatial and temporal reasoning. If a model understands how objects are arranged in space and how they interact over time, it's much less likely to be fooled by adversarial attacks. It can see through the superficial changes and recognize the underlying structure of the scene.
Okay, yes, and let's delve into the Enigmata project a bit more. Specifically, how might synthetic verifiable puzzles, like those used in Enigmata, help us move beyond this Potemkin understanding? What's the potential there?
The beauty of Enigmata's approach is that it forces the LLMs to actually reason rather than just regurgitate information. The puzzles are designed to be verifiable, meaning there's a clear and unambiguous way to check if the model's answer is correct. This pushes the model beyond simple pattern matching and requires it to engage in logical deduction to arrive at the solution.
Exactly, and the fact that the puzzles are synthetic allows for a much greater degree of control and experimentation. You can systematically vary the complexity of the puzzles, the types of reasoning required, and the amount of information available. This allows you to probe the model's capabilities in a much more targeted way than you could with natural language data.
And the verifiability aspect is crucial. It provides a clear signal of whether the model is actually understanding the underlying logic of the puzzle or simply memorizing patterns. This allows you to track the model's progress over time and identify areas where it's still struggling.
So it's a more rigorous way to evaluate the internal validity of the reasoning process, not just the correctness of the output. That's key. It's not enough for the model to get the right answer. It needs to be able to explain why it got the right answer, to demonstrate that it actually understands the underlying logic.
And because the puzzles are synthetic, you can generate an unlimited number of them. This allows you to train the model on a massive dataset of structured reasoning problems, which can help it to generalize to new and unseen puzzles.
But even with synthetic puzzles, I think it's important to consider the limitations. Are we sure that the types of reasoning required to solve these puzzles are representative of the types of reasoning required to solve real-world problems? Are we inadvertently creating a system that's really good at solving puzzles, but still lacks the kind of common sense reasoning that humans possess?
That's a valid concern, and it highlights the need for a diverse set of puzzles that cover a wide range of reasoning skills. We need to make sure that we're not just training the model to excel at one particular type of problem, but that we're building a system that's capable of general-purpose reasoning.
And I think it's also important to consider the level of abstraction at which the puzzles are presented. Are they presented in a symbolic form, or do they require the model to translate from a perceptual representation to a symbolic representation? If the puzzles are presented in a symbolic form, we may be missing a crucial aspect of real-world reasoning, which is the ability to extract relevant information from sensory data.
So you're suggesting that we should incorporate more perceptual elements into the puzzles, perhaps by presenting them as images or videos rather than as text.
Exactly. That would force the model to engage in perceptual reasoning as well as logical reasoning, which could lead to a more robust and general purpose reasoning system. It's about bridging that gap between perception and cognition, between the raw sensory input and the abstract symbolic representation.
That's a great idea. And it also raises the possibility of using these puzzles to probe the model's understanding of the physical world. We could create puzzles that require the model to reason about the consequences of physical actions, such as pushing a block or pouring water from one container to another. This could help to address the embodiment problem that we discussed earlier.
And it could also help to reveal the model's understanding of spatio-temporal relationships. We could create puzzles that require the model to track objects over time and to predict their future locations based on their past movements. This could help to build AI systems that are capable of true spatial and temporal reasoning.
One thing to keep in mind as well, the method by which synthetic puzzles are generated might unconsciously add bias. It's important to make sure that we don't create puzzles that are unconsciously designed to favor certain types of reasoning or certain architectures. The puzzle space itself needs to be carefully explored to avoid unintended consequences.
That's an excellent point. Even the process of creating the puzzles requires a kind of intelligence. And so there is a real risk of creating a feedback loop rather than generating truly novel reasoning.
Reflecting on it, the core of the issue might not be about data volume, but data diversity and the verifiable nature of the learning. What if we designed data sets that explicitly target the limitations observed in Potemkin understanding? What would that look like?
That's a smart approach. Instead of just blindly throwing more data at the problem, we need to carefully curate data sets that expose the model to the kinds of situations where it's most likely to fail. This would allow us to identify the weaknesses in the model's architecture and to develop targeted solutions.
For example, we could create datasets that contain a large number of examples of common sense reasoning problems, such as the Winograd Schema Challenge. These challenges require the model to understand the relationships between different entities in a sentence and to make inferences based on its knowledge of the world.
We could also create datasets that contain a large number of examples of spatial and temporal reasoning problems, such as tracking objects over time or predicting the consequences of physical actions. These datasets would force the model to develop a more robust understanding of the physical world.
And we could design the datasets to be inherently verifiable so that we can easily assess whether the model is actually understanding the underlying concepts or simply memorizing patterns. This would allow us to track the model's progress over time and to identify areas where it's still struggling.
One way to do that is to incorporate adversarial examples into the datasets. These are examples that are specifically designed to fool the model, to expose its weaknesses. By training the model on these examples, we can make it more robust and less vulnerable to adversarial attacks.
Another approach is to use synthetic data, as in the Enigmata project. This allows us to generate an unlimited number of examples that cover a wide range of different situations. And because we're generating the data ourselves, we have complete control over its content and structure.
But again, it's important to be mindful of the potential biases that can creep into synthetic data. We need to make sure that we're not inadvertently creating datasets that favor certain types of reasoning or certain architectures.
Right. The key is to create data sets that are both challenging and representative, that push the model to its limits while also reflecting the diversity of the real world. It's a delicate balance, but it's essential if we want to move beyond Potemkin understanding and build AI systems that truly understand the world.
It also points to the need for better evaluation metrics. We need to move beyond simple accuracy scores and develop metrics that can assess the model's understanding of the underlying concepts, its ability to generalize to new situations, and its robustness to adversarial attacks.
I agree. We need to develop metrics that are more sensitive to the nuances of understanding, that can distinguish between a model that's simply memorizing patterns and a model that's actually grasping the underlying principles.
And we need to develop metrics that can assess the model's spatial and temporal reasoning abilities. This could involve creating benchmark tasks that require the model to track objects over time, to predict the consequences of physical actions, or to navigate through a virtual environment.
And I think it's important to develop metrics that are interpretable, that can provide insights into the model's internal workings. This would allow us to understand why the model is making certain decisions and to identify areas where it's still struggling. You know, what you've both pointed out about needing to explore the internal representation is so important.
And that really gets to the idea of transparency. If we're going to trust these AI systems to make important decisions, we need to be able to understand how they're making those decisions. We need to be able to open up the black box and see what's going on inside.
Exactly. And that requires a fundamental shift in how we design and evaluate AI systems. We need to move away from opaque black box models and towards more transparent, interpretable models. We need to build systems that are not only accurate, but also understandable.
Which brings us back to the importance of neuro-symbolic integration. By combining the strengths of neural networks with the strengths of symbolic AI, we can create systems that are both powerful and interpretable. We can build systems that can learn from data, but also reason about the world in a way that's similar to how humans do.
Okay, well, I think we've thoroughly explored the concept of Potemkin understanding and its implications for the future of AI. It's a challenging but ultimately rewarding area of research, and I'm optimistic that we can make significant progress in the years to come.
Yes, it's a crucial step towards building AI systems that truly understand the world, systems that are not only intelligent but also reliable, robust, and trustworthy.
And systems that can help us to solve some of the world's most pressing problems, from climate change to disease to poverty.
So, let's continue to push the boundaries of what's possible, to challenge the assumptions of current approaches, and to strive for a deeper understanding of intelligence itself.
Indeed. And with that, we bid farewell. Thank you for tuning in to Cognitive Spirals. We look forward to spiraling with you again next time.